Hello everyone, this is Mukul Sharma. I'm from IIT ISM Dhanbad and this is my entry for Digital Rocket Design Challenge 2021. So this is what my design looks like. I call it Shaurya. So what I have done is I made a single stage rocket but with a cluster of three engines around it. These three engines, as you can see here, these are the three engines. The engine 1, engine 2, engine 3. Engine 1 and engine 3 are the same engines which can help the rocket. And this is the side view, this is the 3D unfinished view, and this is the back view. First, let's see what my rocket actually looks like. This is what my rocket looks like. Its name is Shaurya. This is the nose cone. The payload is 100 grams. This is the body tube. This payload is 100 grams, which is twice this specified payload. It contains this is the body tube. It contains a shock cord, a parachute, a warding, and then we have a transition. This transition is a 1.5 inch and 0.5 inch long and 2-inch wide transition. It is a quite common transition which we can find everywhere. Uh, this is then the third body tube, which contains the cluster of three engines. And I know you will say that the open rocket doesn't really support the pod concept, but let me explain it later. And it also contains the freeform fin set here, which you can say this is a freeform fin set. There are four total number of fins. The fin cant is around 2 degrees. This is the shape of the fin. This is the clear shape of the fin. It will be made of basswood. And then this is the launch lug. Launch lug is placed as close as possible to the center of gravity because this is what we actually do. Now let's see at our presentation. General idea in this design, I try to provide you with the best and most efficient design possible. And I have to fully use the restriction. I use 3 G-class motor in a cluster, and I did simulation. I made this on Open Rocket, and I did a confirmatory simulation on Roxen. These are the component of a rocket. There are essentially four components: the nose cone, body tube, engines, and fin set. First, let's talk about the nose cone. The nose cone is a conically shaped forwardmost section of the rocket. It is used to minimize aerodynamic drag. And in this design, this nose cone is actually the payload bearing stage. So when we join this nose cone with the body, we need to provide it. We need to provide a really strong shock cord, which can withstand the immense amount of force which it will face when at the time of ejection. The material used in nose cone is PVC. Its shape is given here. Is a ogive shape. It contains a shoulder. The shoulder's length is around 1.5 inches, which is equal to the diameter. And the shape parameter is 1. The weight is approx 47 gram without payload and 147 gram with payload. The dimensions are given below. Length is around the 4 times the diameter, which is well according to the general convention, which says the length should be around 3 to 5 times the diameter, and the thickness is 0.08 inches. Let's talk about body tube, and it forms the main body of the model rocket, and it holds the nose cone and fins in place. I have in this design I've used two body tubes and I connected them with a transition so that it gives me a broader deck at the end of the rocket. And it houses the parachute, the shock cord, the boarding, and the launch lug. Here we can see the material, the specification of our body tube. Material uses paper. Thickness is 0.08 inches. The diameter and the length are given below, and the weight is also given here. These are the two body tubes, and I connected them with the help of a transition. And first body tube houses the shock cord, parachute, and boarding. I told you that we need a very strong shock cord. So here it is. It's a 1-inch thick shock cord. It is the strongest shock cord available in Open Rocket Simulator. And then we have the parachute, which is a 10-line parachute, which is also very strong parachute. And then we have a boarding. Boarding is used to protect the parachute from the oncoming ejection charge. And then the second positive houses are our primary engine, which is G35EJ. Then let's talk about the fin set. The fins are used to provide stability to the rocket, and in this design we used a freeform fin set, and it is made of basswood. And there are total number of fins are 4. Fin cant is around 2 degrees. Fin cant is given to the rocket so that it rotates when it goes up. In our condition, it really helps us because we need this rocket to reach the maximum height. We do not need it to maneuver in the x direction, in x or minus x or z direction. So here we can say that we needed to give it a cant so that it rotates when it reaches up, and it it scales at greater height, at a larger height, and its weight is around 30 gram. The fin set's weight is around 30 gram. Now let's talk about the engines used. There are three engines used. Two engines are G142 type, and one engine is G35EJ type. The total propellant weight is 124.7 gram, which is approximately 125 grams, which is under well according to the limitations given issued to us. The total impulse is 269 Newton seconds. Now let's talk about CG, CP, and static margin. The center of gravity, as calculated by the software, is around 18 inches from the tip of nose cone, which is, I think, correct. And now the real pickle comes when we talk about the center of pressure. See, what I came to know is open rocket can't really differentiate between the inner tube and the outer tube. Oh, I'm sorry, it differentiates between inner tube and outer tube. So when we place inner tube outside, it doesn't really include it in when it calculates the surface area. So when I simulated in open rocket, it gave me somewhat incorrect result. So approximately, well, I needed to approximate it out, but yeah, we can see this. Let's talk about it later. The CP is approximately 22 inches away, and static margin is greater than 2, which is a little bit overstable. Now let's talk about external ports. OpenRocket doesn't really support external ports, but I used two external ports, and and they house two secondary engines. They both house a single inner tube with single engine, and the engine used a G142. And I really wanted to add a nose cone to these external ports. It will really help at the time of the flight, because currently the air hits the blunt side of the inner tube, which is not that good aerodynamically. And let's talk about this simulation. Apogee is far greater than 14. It's around 1400 meter, and I am talking it in the safe side. Okay, weight of the rocket is around 700 grams. Static margin is greater than 2 caliber. Payload is 100 grams at nose cone. Time of flight is around 140 seconds. The grounded velocity is around 11 meter per second, and maximum acceleration you can see here. And it's approximately zero point 0.8 Mach rocket. Now let's look at some plots. Let's wait. Let's look at plot in open rocket. So this is my rocket. Now let's look at flight simulation. This is the main simulation which we need to see. Two G14211 rockets and G35EJ11 rocket. Let's run it again. Now it says no warnings. So the apogee is 1355 meter as given by open rocket. See, the thing is, open rocket doesn't really do that well in case of external ports. It is not that correct. So, but let's see. Let's plot it out. This is the total motion versus time plot. Here you can see. Let me zoom in. This is what it looks like. Now let's see stability versus time. You can see my caliber value. Really sorry. So this is our caliber value. really sorry. It's giving me some hard time. Yeah. Now let's look at these. The maximum caliber value is around 3, which is overstable. And well, you can see it here. This is my stability versus time plot. Now let's see what else can we see. Let's see total motion versus time. The total motion versus time graph. Now, anything else? Yeah, yeah, fights right side profile. You can see here. Wait. This is what it looks like. 220 meters is the x direction displacement. Now, drag coefficient versus Mach number. This is what it looks like. This is 0.8 Mach. The highest value is given as 0.8 Machs. Now, let's head back to our slides. No. Let's wait. Let's see at what Proxim tells us. So what I did is I exported the same file to Roxim as .rkt file because I thought that OpenRocket isn't giving me some really good simulations. So this is what my rocket. This is what the same rocket in Roxim looks like. This, you can see mass is 100 gram and all things are same. But one thing that we should see is here it uses primary engine of G33J12. The reason behind this is G35EJ engine is not available in Proxim software. So I had to swap it with the G33J. These two engines are approximately similar. Okay, now let's launch this engine. This is quite shocking. I was really shocked when I saw this. So I don't really know which way should I believe. Should I believe Roxim or should I believe OpenRocket? It says that the apogee is 1858 meters, and it says the maximum acceleration in G's is 56.88. You can see it here, and let's plot it. Velocity acceleration graph. So this is what it looks like. According to me, this Roxim is giving me somewhat similar simulations because the reason behind it is this really Roxim supports external pods. Roxim really supports external pods, but OpenRocket doesn't really support external pods. So I have given a OpenRocket says the apogee is for 1356 meter, and it doesn't really support these two things. But Roxim says that the apogee is around, where is it? Right simulation. My apogee is 1856 meters. Okay. Now let's see. Let's head back to our presentation. These are the plots given by OpenRocket, which you already saw. Some important points. Transition. I used a 1.5 to 2 inch transition, which is easily available online. Payload. I used a payload of 100 grams instead of 50 grams. All materials I choose are I chose all the materials after a thorough research on the internet. Fins, yeah, these are free-form fins which can be easily reproduced on Westwood. And there is quite a large difference between simulations done by OpenRocket and Roxim, but they both produce apogees of at least 1350 meters. I think the simulation done by Roxim is a little bit more correct and a little bit more, I don't know what to say, existential, I don't know, a little bit more correct. Well, we can say that the simulation done by Roxim is a little bit more correct than OpenRocket because Roxim supports the concept of external pods, but OpenRocket doesn't really support the concept of external pods. But still, if we consider the worst case situation, if we all consider OpenRocket instead of Roxim, we get apogee of around 1350 meter, which is quite good. Thank you very much. And if you have any questions regarding my design, please hit me up. These are my contact details. Thank you. And thank you very much for giving us this opportunity.